Guiding your kids through the world of math is such a fantastic adventure. Those moments when things click are just, they're unbeatable.
Oh, absolutely.
But we also know that sometimes maybe you glance ahead in the curriculum and a topic might look a little mathematically mysterious.
That's absolutely right,
Mm.
especially when you're looking at something like complex numbers. Maybe in the math map for your 7th graders, it can seem like quite a leap.
Exactly. That's what we're diving deep into today. We're
Yeah.
going to explore complex numbers, specifically in the context of the math map. Our aim is pretty simple, really. Just
Mm.
make these ideas crystal clear, genuinely interesting, and totally relevant for both you and your curious 7th grader.
Think of it as your backstage pass.
Understand it before you even open the math map together.
And it's so important to remember that the materials in curricula often draw from these really rich historical approaches to math, like the Quadrivium. It provides incredible depth, but it can sometimes feel a bit dense when you first hit a new concept.
Definitely.
So our goal here is just to gently unpack one of those concepts, complex numbers, and make it feel much more approachable.
Couldn't agree more.
At its heart, a complex number is really just a clever way of putting two different kinds of numbers together.
Okay.
So you're familiar with real numbers, those everyday numbers on a number line, the ones you've been working with all along.
Right, like 3 or 5 or 0.5.
Now imagine introducing a new type of number, an imaginary number.
Imaginary. That still sounds a bit like make-believe. What makes them imaginary?
The real key, is this special symbol, the letter I. Think of I as a unique tag or a label. When you see it attached to a number, it just signifies that this part of the number has some special properties that regular real numbers don't have.
So it's like a little flag saying, handle this differently. Thanks to this I tag, we've got these two parts, a real part and an imaginary part. How do we even work with them? Where do they exist?
That's a great question. And that's where the idea of the complex plane comes in. It's really neat.
Complex plane.
Instead of just one number line stretching out left and right, imagine a whole flat surface, like a piece of graph paper.
Okay.
This is the complex plane. It's a two-dimensional space where these complex numbers live.
So if it's a flat space, like graph paper, what do the lines represent?
Good question. The horizontal line, the one you're used to as the x-axis,
Yeah.
that represents the real part of the complex number. All those familiar real numbers live along this line.
Standard number line horizontally.
Okay.
Makes sense.
And the vertical axis, the I-axis.
That must be where the imaginary part hangs out, right?
You got it.
Yeah.
Exactly. The vertical axis is where the imaginary part of the complex number is represented. So any complex number, it has a value along the real axis and a value along the imaginary axis.
Ah, I see.
You can think of it like finding an address on a map, right?
Yeah.
A single point on this complex plane tells you everything about that complex number, both its real part and its imaginary part are baked into that one point.
That's a great way to picture it, like coordinates. Each complex number has its own unique address. So now, what happens when we start doing basic math? Let's talk about adding them. How do you add these two-part numbers?
Adding them is surprisingly straightforward, actually.
Oh, good.
Remember, they have that real part and that imaginary part flagged by the I. When you add two complex numbers, you simply add their real parts together, and then separately, you add their imaginary parts together.
Oh, so you just keep them segregated.
It's like keeping apples with apples and oranges with oranges. You combine the real bits, and you combine the imaginary bits.
So the real stuff stays together, and the imaginary stuff stays together.
Think back to our map analogy. If one complex number is, say, 2 steps right and 3 steps up, imaginary,
Okay.
and another one is 1 step right and 1 step up, adding them together just means you've moved a total of 3 steps right, that's 2 plus 1,
Right.
and 4 steps up, that's 3 plus 1. You're just combining the horizontal moves and the vertical moves independently.
Okay. Okay, that doesn't seem too scary at all. Adding is manageable. Now, what happens when we multiply complex numbers?
You're right, multiplication introduces a really fascinating twist. It's got layers.
Uh-oh.
No, it's cool. So first, if you just multiply a complex number by a regular real number, like just multiplying by 2 or 3,
Yeah.
you're essentially just scaling it, making it further away from the center of our complex plane, the origin, where the axes meet, or maybe bringing it closer if you multiply by fraction.
Okay.
But it stays pointed in the same direction.
Like zooming in or out on our map point, but you're still looking at the same landmark.
Perfect analogy. But
Yeah.
when you multiply two complex numbers together,
Here we go.
something really interesting happens. You get both that scaling effect, stretching or shrinking, and a rotation.
Rotation. Whoa.
Yeah. The resulting complex number will be at a new distance from the origin and at a new angle.
Rotation. Can you give us a concrete example? How does that rotation bit work?
Absolutely. Let's go back to that special imaginary unit, I. Remember our tag?
Yep. The flag.
If you take any complex number, any point on that plane, and multiply it by just I, its position on the complex plane will rotate by exactly 90 degrees counterclockwise around the origin.
Wow. Just multiplying by this one little I turns the whole thing a quarter of the way around.
Exactly. A 90-degree spin, just like that.
If you multiply by I, again, like I times I.
If you multiply by I a second time, which is the same as multiply by I squared, or I, you get another 90-degree rotation. So in total, that's 180 degrees, a complete half turn from where you started. Multiply by I a third time, that's another 90 degrees, so now you're at 270 degrees around. Yeah. And finally, if you multiply by I 4 times, well, that's 4 90-degree turns, which is
360 degrees, back where you started.
exactly a full 360-degree rotation. You're right back to the original number.
That's such a vivid way to see each I multiplication just gives the number a little spin on the plane. It almost makes this abstract imaginary part feel like it has a real physical effect on its position.
It really does. And this hints at another really useful way to describe complex numbers.
Oh.
So far, we've been talking about their position using the horizontal and vertical imaginary parts, like giving map coordinates, right? East, west, north, south.
Yeah, like the address.
But there's another way called the polar form.
Polar form. Okay, what's that all about?
Instead of saying how many steps across and how many steps up to get to our point on the complex plane, polar form describes it by its direct distance from the origin. How far it is from the center point and the angle of that line, the angle it makes with the positive real axis, our horizontal starting line.
Oh, so instead of giving an address with street and avenue, it's more like saying, go 5 miles in that direction.
Precisely, like saying walk 5 meters at a 30-degree angle, distance and direction.
Okay.
And this way of representing complex numbers, it makes that multiplication idea even clearer or maybe more intuitive.
How so?
When you multiply 2 complex numbers described in this polar form, distance and angle, you just multiply their distances together.
Okay.
And you add their angles together.
That makes the scaling and rotation so much more obvious. Multiply the how far, add the which way. Wow, that's really elegant.
It really, isn't it?
Yeah.
It tidies things up beautifully. Now, all of this might still feel a little bit like we're just playing with abstract ideas on graph paper.
Yeah, a little bit. It's cool, but...
Right, so let's connect it to the real world.
Yeah.
Why should a 7th grader, or you as their teacher, really find complex numbers interesting and relevant? Where do they actually do anything?
Yes, please. Let's bring it down to earth. Where do these seemingly imaginary numbers actually show up in our lives?
One really significant area is in the world of electricity, specifically with alternating current or AC circuits.
AC, like the power from the wall outlet.
Exactly. The electricity that powers your lights, your phone charger, pretty much all your home electronics. It doesn't flow in a constant stream. It actually oscillates. It waves back and forth.
Right.
Complex numbers are an incredibly powerful tool for engineers working with AC. They allow them to represent and analyze both the strength of the signal, we call it the magnitude, how intense it is.
Okay, the power level.
And the timing, which we call the phase, like where the wave is in its up and down cycle at any given moment. Is it at its peak? Is it at zero?
So strength and timing.
Yes. Both pieces of information captured within one neat mathematical package, the complex number. It simplifies things enormously for electrical engineers.
So when engineers are designing everything from our, toasters to the entire power grid, they're actually using complex numbers to understand and control how that electricity behaves. That's incredible.
Absolutely essential. Couldn't do modern electrical engineering without them.
Yeah.
Another key area is in various fields of engineering that deal with movements and vibrations.
Like what?
Think about designing car engines to run smoothly, or analyzing how a bridge might vibrate in the wind, or even understanding the complex vibrations of a musical instrument's strings to improve its sound. Complex numbers provide a really simplified and, again, visual way to handle these kinds of dynamic oscillating systems. They help engineers understand the different frequencies, the amplitudes of vibrations. It makes designing things much more effective and stable.
That connection to real-world design, making things work better, that's really powerful. Anything else? Maybe something unexpected.
Definitely. And this one is really beautiful. Believe it or not, complex numbers have this amazing, unexpected connection to art and nature through something called fractals.
Fractals, like those super intricate, mesmerizing patterns?
Many of those stunning visuals are actually generated using relatively simple mathematical formulas. Formulas that involve complex numbers, just repeated over and over again.
No way. way, fractals come from complex numbers. I had no idea they were the secret ingredient. They look like crazy art, but sometimes natural things too.
They are. And what's truly fascinating, like you said, is that these mathematical patterns often mirror patterns we see in the natural world. Think about the way a fern frond branches out,
Oh, yeah.
or the intricate six-sided structure of a snowflake, or even the jagged shape of a coastline. So complex numbers aren't just abstract tools for technology. They also connect us to the inherent beauty and complexity we see all around us in nature. It's a wonderful example of how seemingly abstract math can underlie very real, very visually striking phenomena.
That's incredible.
Think about a simple math with these two-part numbers done repeatedly, creating these infinitely detailed and beautiful designs.
That's absolutely mind-blowing. Okay, we started with this idea of two-part numbers living on a 2D plane.
Yeah.
And now we're seeing how they're fundamental to things like our electricity, engineering designs, and even the breathtaking beauty of fractals in art and nature. It really changes how you think about them, doesn't it?
Exactly. That was the goal today, to take that initial concept of complex numbers, which, yeah, can sound pretty abstract, and reveal how they're actually incredibly powerful tools with very tangible, very real applications in the world around us. For you as homeschool parents, hopefully this understanding can make introducing these ideas to your seventh graders much more engaging and meaningful.
Definitely. So just to quickly recap for our listeners getting ready to guide their students through this in the math map, we've learned that complex numbers are basically a combination of a real part and an imaginary part, thanks to that special marker, I. We can picture them as points on a 2D map, the complex plane. Adding them is straightforward. Add the real bits, add the imaginary bits.
Keep them separate.
And multiplying them, that's where the magic happens. It involves both stretching or shrinking their position and rotating them on that plane, which makes even more sense when we think about distance and angle using that polar form idea.
You nailed it. And the crucial takeaway, I think, is that these aren't just theoretical ideas stuck in a textbook. They are fundamental. They're fundamental to understanding and designing the technologies we rely on every single day, and even to appreciating the intricate beauty found in both art and the natural world.
For all of you homeschool parents out there getting ready to explore complex numbers with your seventh graders using the math map, remember that at their core, these numbers are about understanding quantities that have two different aspects working together, like a magnitude and a direction, or those real and imaginary components. And as we've seen today, that kind of two-part idea pops up in all sorts of surprising and important places.
Which raises a really interesting point to maybe leave you thinking about.
Oh.
How many other seemingly abstract mathematical concepts, things that might look strange on paper at first, might actually be the hidden keys to understanding and explaining the world around you?
Definitely something to chew on. Thanks so much for taking this deep dive into complex numbers with us today and helping shed so much light on what can feel like a really, well, complex topic.
Is this love?